the second part. Now we are considering how to transfer the strain on the top left-hand side surface, okay, into a resistance change, okay. So we are going to use a piezoresistive, the sensing method for the measurement. Okay, so now we consider a block of a resistor. When the block resistor, if we compress, okay, the resistor, so the structure will change, okay. So not only the length change, but the width and the thickness will also change as well. So when you push the material in this direction, so the material will become shorter, the structure becomes shorter, but it will become higher, taller, and wider at the same time, okay? Yeah, is it easy to understand? Okay. However, the degree for the length change and the width change will be different. There will be a ratio between the width change and the length change. The ratio we call the Poisson ratio. That means you push down the length change like 1 if of a large case. That means the width change will be only 0.3, not 1. Okay? So the Poisson ratio is very typical for most of the material. Most of the material has a different kind of Poisson ratio. The Poisson ratio will be ranging from like 0 to 0.5. Only some material will be more than 0.5, but most material will be in this range. But some material is 0. Okay? What kind of material? Have you ever seen material with a Poisson ratio of 0? That means you push it down, it will not expand at the width. What kind of material in your mind? Okay, just give you one, okay? One example, like a cork. Do you know cork? 软木塞. Cork. When you drink like a red wine, you see there's a cork on the bottle, right? On top of the bottle. That kind of material is a 0 Poisson ratio material. When you push it down, it never expand, right? It's important when you push down the cork things into the bottle. If we expand too much, it'll give a lot of pressure inside. So you want to keep the same structure on the top and the bottom. Only change the shape. A special material, but most material do have a different kind of Poisson ratio, ranging from 0. something to 0.5. So usually we'll give a number of 0.3. 0.3. Okay, so we have this kind of compression of the material in length. So the material will give a resistance like this. So the resistance of this kind of structure will be equal to the resistivity, though, times the length of the material over the cross-section of the material. Okay. So that means if you want to have a high resistance, we can have very low material, okay, and high resistivity of the material as well. And if we increase the cross-section, actually we will reduce the resistance of the material. Okay? Yeah. So the resistance will be proportional to the length, inversely proportional to the cross-section. A times B is cross-section of the material. Okay, now we consider this not a fixed structure. We push it into a shorter and a wider structure. So now the resistance will be changed accordingly. Okay, so when we do this kind of, if we consider only the structural change, if the resistivity is not changed during this kind of squeeze, so the length will become smaller. A and the B will become larger, longer, or wider, right? So, so we consider how to express this by using the strain. So, for example, the delta L, the length change, will be equal to the strain times the total length. That's a final definition. Okay. Okay. The strain can be considered as a stress over your Young's modulus. Right? Okay. It's a final definition as well. Epsilon equal to sigma. Sigma is the stress over Young's modulus. It's a Hooke's law. Okay. So you have a stress and the stress over the Young's modulus, like a spring constant, you will find out the strength, like a displacement of the spring. Okay, very similar. And for the width, because the width, we have a strength for the length, epsilon. So the strength for the width will be the strength times the Poisson ratio, mu. It's not 1, okay? The Poisson ratio will be, for example, 0.3. So the strength for the width or the height change will be smaller than the change of the length, okay? So this is the ratio we are talking about. We just talked about the Poisson ratio. Poisson ratio is mu times epsilon. Epsilon is the original strength of the length in the length direction. And the sensing, the width change will be the Poisson, the strength times the Poisson ratio, epsilon times mu, and times the original length. Then we replace the epsilon, the strength, by using the stress over the Young's modulus. Okay. Now the final structure will be, because on the top we need to have the length. So the length will become shorter, will become L minus delta L, right? So minus delta L will be the minus sigma L over E. So they share the same length L, so we can take out the L, and it finally become 1 minus epsilon, 1 minus epsilon times L, the top part. So now the new resistance, the top part, the length becomes shorter, a little bit shorter, okay? So it becomes length times 1 minus epsilon, the strength. On the bottom become longer, not longer, become wider or taller. The A times epsilon times mu, because the Poisson ratio indicates the width, the increase of the width is not as the same as the length. Yeah, it has some deduction by times the Poisson ratio. Okay, epsilon times mu. If mu equals 0.3, that means you got the strength on the height or on the width is only like a 0.3, like 30% only of the strength on the length, in the length side. Okay. Yeah. So on the bottom it become wider, taller, and wider. Okay. So finally, because these are equations are very complex, so we can use interior expansion and to make it simpler to take the first two terms. You can find out to see these final results like this. Okay, and if you replace this by a gauge factor, the gauge factor means how much strength change in order to change your resistance. Okay, the ratio between them, we call the gauge factor. So if you have a large gauge factor, that means you have a higher sensitivity of your sensor. So for different strength, for unit strength, you got a more resistance change if you have a larger gauge factor. So gauge factor here is important to indicate how sensitive your piezoresistive sensor is. So higher gauge factor means more sensitive of your sensor. So now we consider the original, this equation, we have developed this kind of relationship. Now we plug into this part and to find out the gauge factor. So after you delta R means R epsilon minus R0, okay? So you just rearrange this equation into this form. You find out the gauge factor is only 1 plus 2 mu. Mu means Poisson ratio. Consider Poisson ratio is only 0.3. So now your gauge factor is only 1.6. It's not very high. That means you have a 1% of the strength change. You also got a 1% of your, like 1.6% of your resistance change. Not very high. Let me say it again. If you got a 1.6, the physical meaning is if you have a 1% strength, you got only 1% resistance change, 1.6% change at the same time. So the enlargement ratio is not large. So if we use the metal thin film as your sensor, this is the result you will get. The metal film cannot become a good sensor as a piezoresistive sensor. The gauge factor is small. So in order to enlarge the gauge factor, people think when we do the pushing process, currently we consider only the structural change. If the pushing process also change the resistivity of the material, it may greatly increase the gauge factor. Okay, consider we don't think of the change of the piezoresistivity when we are doing this equation development, right? But now, if we consider the dou also change during the pushing, so the gauge factor will become large. So if we consider dou change, we need to input the dou change here, okay, during the squeeze process, and we can get a new equation of the R epsilon, okay. So if we consider using like silicon, compared to metal, silicon is a better material as a piezoresistive material because when we squeeze the metal film, the resistivity never change. But when we squeeze on the silicon, especially doped silicon with a p-type, either p-type or n-type doped silicon, the resistivity will change in addition to the structural change. So this change will give a gauge factor, the maximum gauge factor, even up to like 200. It's much larger than 1.6 when you consider only the structural change. It's much larger. It's almost 2 magnitude, the order magnitude is larger, 100 times larger. Okay? So n-type and p-type also have different opposite sign. So n-type will become negative due to a variety of factors. The gauge factor polysilicon film is typically an order magnitude lower than single crystal films as well. So the 200 is considered we're using the single crystalline silicon, using the silicon substrate, okay? So that's why in the past, when we are talking about the bulk machining, we talk about a special method. We call the etch and stop, right? So by using etch and stop technique, you can preserve some structure on the single crystalline silicon as a sensor. Because single crystalline silicon substrate can give you a very high gauge factor. It's become a very good sensor. But in our case, we are not using single crystalline silicon. Actually, we are using polycrystalline. For polycrystalline silicon, it's not that high. It's ranging from 15 to 25. It's one order of magnitude lower than single crystalline silicon. However, it's still one order of magnitude higher than only using the structure change. Remember, structure change gives you only 1.6 gauge factor. But by using polysilicon, you can have 15, even 25. Much larger. Okay? And another thing about the sign is the n-type, p-type silicon have opposite sign, n-type being negative. Okay, so so when you are doing this kind of calculation, you think of when you squeeze the film, and the piezoresistivity will be increased. Actually, the sign is negative. For p-type polysilicon is -15, and p-type is positive. The sign is positive. When you extend the structure, the rho will increase. And for n-type silicon, when you do extension, the gauge factor, the rho will be decreased. It's opposite. Okay. So when you do the squeeze, okay, now we consider here. So we have two positions. You can put the sensor on the top or on the bottom, right? On the top you have extension. On the bottom you have a squeeze, right? Compression. So if we have put the negative type piezoresistor here, so when we do the squeeze, so he will give you positive results. So the resistance will increase when you squeeze the film n-type on the bottom. The resistance will increase. But if you put the p-type here, the resistance will decrease. Okay, they will share the same sign. There's differences. And also, N-type, P-type, they have different sensitivity, and also they have different sensitivity on the tension and the compression, different kind of encounter different kind of stress. They have different value. I cannot remember. P-type is more sensitive to the extension or to the compression. I cannot remember. I think one of them is more sensitive to the tension, the tensile. And the other one is more sensitive to the compression. Yeah, another saying here, so we need to go back to the literature to find it out. Yeah, but they have some differences, okay? So when you are choosing different types of the material, you need to consider the position as well. Different position give you different the sign, different direction of the stress or strain, which can give it different value of the gauge factor. Okay. Okay. Now we consider, okay, because our sensor is put on a portion of the surface, it's not positioned at one point, right? It's a certain kind of length. So the sensor will cover not only at one point, but a certain distance. So from this point to this point, actually the bending moment or the curvature will be different. So that's why we need to average out the output signal, okay? So the bottom equation just gives the average strain along the surface when your sensor have a certain kind of a length. It's a finite length, it's not a small point, single point, finite length. So the equation is coming from, you add out the top and the bottom value divided by 2. That's it. Just average out, yeah, across this surface. You get a final equation here. So LG means the length of the sensor. LB means the length of the beam. Okay. So this is a maxima value at the base. Okay, and the average is a little bit smaller than epsilon maxima. Okay. Okay. So now by using the transformation from the piezoresistive effect, you can transfer the strain, the length change, into the resistance change. Okay, so the final equation will be like this. The resistance change will be proportional to the gauge factor. So gauge factor is important. So you have 100 here, you got 100 times enlargement, magnification, application. And also times the length of the beam and also the distance from the center. Okay, the A means the thickness. Okay, the thickness. So if you have a thicker beam, it can have a larger signal. Okay, because you put the sensor on the top surface, you have got the more strain on the surface. Okay, and at the base, you got a more bending moment. So also got a higher signal here. Okay. Okay. So after understand the signal out, so we're almost done. Yeah. After we transferred this one into voltage, we got the final results. That final result will be important not only for your homework but also for your midterm, the second midterm. So in the second midterm, we will give you those equations. You don't need to memorize the equation. I give you the equation. But you need to understand how to use the equation to do your final design. That's the important part. So you need to understand the meaning of each term and the effect of each term. Okay? Now, so after you understand the signal output, then we consider the next topic about the diffraction of the beam. So in the previously, we just consider the beam itself. Now we connect the proof mass back into the whole system. So after diffraction of beam, so here we assume the proof mass won't change the structure. Only the beam will diffract. The proof mass won't because it's thicker. Okay? So when we have this kind of diffraction of the beam, so there will be a distance between the original position to the tip of the beam. And along this direction, we have a proof mass will be extend from this angle to the distance here. So there will be the total distance from here to here. Okay, so the total distance will be the deflection of the beam plus the extension from here to here. So these two, we add these two deflection together, we find out the total difference of the tip of the proof mass to the original position. Okay? So the deflection of the beam is easy. We just plug into the equation, and we using L to replace X, we can find out the beam, okay, LB equal to the final result here. So deflection of the beam tip is here. Now we will consider the angle from the tip of the beam to this kind of extension of the proof mass, and try to find out what kind of a distance between here and here. The distance difference in height. Okay, from here to here. Okay, so now we consider the theta, the angle at the tip, and the theta angle, that means the tangent theta, similar to tangent theta, is equal to this equation. So the final deflection of the tip at the end of the proof mass will be the deflection of the tip plus the theta times LP. LP means the length of the proof mass. That means the tangent theta times the length. You got the displacement here. So the total displacement will be this part plus this part. Is it easy to understand? This part, this part. So you got a total displacement here. Okay, so the second part will be theta times LP, the tangent theta times LP. You got the height difference from this end to this end. The height difference here is equal to tangent theta. The theta is the angle here. It's not easy to understand. Okay. Tangent theta times, that's the length. Actually, it'd be better to write it in sine theta, okay? But sine theta is proportional to the tangent theta. It's similar to theta. So the final, this distance will be the tangent theta, the theta times LP. Is it clear? So your total deflection will be this one plus this one. Okay, this one plus this one together.